Hello everyone, it's Justina Habib from STEM Ismailia High School. In this video, we will go through energy conservation and rotational motion. You can study this concept from Survey Engineering Chapter 10, Section 8. So let's begin by considering the relationship between the torque acting on a rigid object and its resulting rotational motion. Why is that? Because it would help us to generate expression for power and simplify the work kinetic energy theorem. So here's some small recap that you need to be familiar with before we begin this video. First of all, if I have a rigid rod that is rotating about its center to make an angle of theta, and I want to calculate the distance that is done by that root over the arc length, which will equal to arc length equal to d theta, a change of theta, times r, the radius of that root. Second, how to make a resolution for the force or to get the y and the x component of that force. We know that f of x is equal to f cosine theta. Theta is the angle that is done by the force, and f of y equal to f sine theta. And last thing is a simple general integration for x. We know that the integration for x equal to x squared over 2 plus c. How did we get that? First, we add 1 to the power and divide by the new power. So here, an integration for x power of 1, we add 1 to make x power of 2 divided by the new power, which is 2, leaves us by x power of 2 over 2 plus c. And integration for a definite interval starting from a ending with b for f of x. Basically, we get the integration for f of x and then substitute by the final minus the initial, leaves us by f of b minus f of a. So let's start our concept. Here I have a rigid object rotates about an axis through the point O under the action of an external force applied at the point B. We know that the work equal to F at a vector times ds, or the work equal to the force times distance, okay? And in this case, that is the force. I will make a resolution for the force, and I will only consider the one that is tangential to the displacement. So here, if I make a resolution for the force on the x-axis will be f cosine phi, and on the y-axis will be f sine phi. And we will only, as I said, consider the one that is the tangential component along the distance. So the f will equal to f sine phi. And for the d of s, as I said, the arc length will be equal, or the radius or the distance from the axis of rotational and the external force, and d theta, the change of the angle that is the object made. Okay, so here we have d work equal to f sine phi or d theta. And I bet you that you can recognize that f sine phi r is the torque or tau. Okay? And now, if I want to get the rate of the change of the work with respect to time that is done on that rigid object under the action of that force, it will equal to the change of the work with respect to time tau, and the change of theta with respect to time. So here we have that expression, change of the work with respect to time is equal to the instantaneous power, and the change of theta with respect to time is equal to omega, or the angular velocity, which leaves us that the power equal to tau, or the torque times the angular velocity. Okay, this in case of rotational motion, but the power is equal to Fv in case of translational motion. Okay. Here we came to the second thing that we need to discuss in this video. So the net work done by an external forces in a rotating systematic rigid object about a fixed axis equal to the change in the object rotational kinetic energy. Let's prove that and start with a rigid object under a net torque model, whose mathematical representation by torque net equal to I alpha. I is the moment of inertia and alpha is the angular acceleration. Okay, We know that the alpha or the angular acceleration is the change of the omega with respect to time, or the change in the angular velocity with respect to time. Okay, I'm gonna multiply that by d theta over 2 theta. Here it have no effect. It is like multiply the equation by 1. Okay, so we have I d omega over d theta times d theta over d time. So we know that the change of theta with respect to time is equal to omega, which leaves us to have I d omega over d theta, multiply that by the omega. Okay, it is the same, but just a bit more arranged. And I'm gonna multiply the whole equation by d theta. Okay, and cancel each other. D theta will cancel here, and here it leaves us by the net torque times d theta. Okay guys, if you have a good memory, I said that tau or the net torque times d theta is equal to the change in the work. Let's see that in the previous slide, that tau or the network equal times d theta is equal to the change of the work. Okay, so here I have the network times d theta equal to the change of the work, which equal to moment of inertia angular velocity times the change of the angular velocity. Okay, that it leaves us with the change of the work equal to moment of inertia omega d omega. I'm gonna put integration for both sides. Okay, I wrote that to make it more simplified for you. So integration starting from omega initial and ending with omega final. The integration will cancel the derivative here and leave only work. Okay, and here it is a simple integration starting from a ending with b for f of x. Okay, first of all, I is a constant, so we're gonna get rid of that out of the integration, and just it will leave us with omega d omega, and consider that f of x or x dx. So the integration for that will equal to omega squared over 2, starting from final initial and ending with final. So to get rid of that sign here, we're gonna first substitute with the final minus the initial, which leaves us that the work equal to half moment of inertia and omega final square minus half moment of inertia omega initial square. And if you have a good memory again, that expression is equal to the rotational kinetic energy. So here the change of the rotational kinetic energy is equal to work. From the start of the proof to the end of that is equal the work kinetic energy theorem for rotational motion. Okay, in our case we have here a non-isolated system. What is meant by a non-isolated system? It means that the work is done on that system of a rigid object, which represents a transfer of the energy across the boundary of that system. Okay, the energy will transfer, and that will appear as an increase in the object rotational kinetic energy. So last slide we have here is the kinematic equation for both the cases, in the rotational motion and in translational motion. It is very important in solving problems. You can go through that by yourself. It is so simple here. Okay, that was all for today's video.